Hello, welcome. Thank you for being with us today. I'm happy to see so many people on site and so many people online for this hybrid CIS Get to Know Your Neighbor seminar series. I'm very delighted to welcome Professor Antoine Bosselut today. He's a tenure track assistant professor and the head of the Natural Language Processing Lab here at EPFL. His talk today is entitled Neuro-symbolic Scaffolds for Commonsense Representation and Reasoning. A brief outline, we have 1 hour in total. Antoine will speak like for 45 minutes, so we have ample time for questions. Antoine also agreed to take your questions online, so if there's anything urgent, maybe raise your hand and we'll try to take them during your talk. Otherwise, put them in the chat, which will allow us then to take them up easily at the end. You can also unmute if you're not on site to ask your questions directly. So one last word before we dive into the presentation. Many thanks, Antoine, of course, for your availability. And once again, to the entire CIS team for setting the event up. Now, Antoine, the screen's all yours.
Oh, thank you. All right, super. Can everybody see and hear me well? Yes, in person. And oh, right, it shows it right there. It's going to be interesting. Very uncomfortable with what's on screen there. All right, well, thanks so much, everybody, for coming today, and thank you to Jan for that wonderful introduction and for inviting me to give this this talk at the okay, we're back, CIS Get to Know Your Neighbor seminar, where I'll tell you a bit about what we're working on in the new NLP lab here at EPFL. Okay, so apparently that does not work as expected. Okay, there we go. So I guess to start, since this is the Get to Know Your Neighbor seminar, I should say a bit about me. Despite this slightly misleading accent, I'm originally from France, though I did spend quite a bit of time in North America in the intermediate. So before here, I had some stops at McGill University, University of Washington, postdoc at Stanford, and was a young investigator at the Allen Institute for AI. And so, if you're wondering what a French person who was born in France, raised in the US, educated in Quebec, and now lives in Suisse Romande sounds like, in French, it's a bit of a mess, but hopefully you'll all get to experience that over the next few years. As Jan mentioned, I joined in the fall here as a PATT and launched the Natural Language Processing Lab, or NLP Lab, which currently includes research on what all these great folks on the slide here work on. So as implied by my lab's name, we work on natural language processing, or NLP, which generally focuses on designing automated systems that perform or enable a wide variety of interactions with human beings using language. So this might include different ways of enabling human-machine collaboration, such as with modern search engines and dialogue agents that allow humans to access knowledge and services with greater efficiency than ever before, or ways of accelerating collaboration between humans by allowing us to automate many of the laborious challenges that hinder communication between humans. So the most obvious application of this is machine translation, which addresses the fact that many of us speak very different languages and are unlikely to learn every other language we don't speak. And finally, NLP is also used to mine insights about humans. So hopefully in the goal of collecting data to better cater to them and provide better products and better services. And so the goal of today is really to introduce you all to some of the research that my lab conducts within the larger field of NLP, and to get you thinking about two questions. The first, how can methods designed for NLP be used in your own research areas? So some of the big successes in NLP over the last few years, such as self-attention, transformer models, large-scale pre-training, have started to move into other areas recently, and it's really just the beginning. So how we can, think about new collaborations into these other research areas. And finally, how can methods from your areas actually be used to improve NLP? So at the end of the day, from an applied perspective, I'm always looking for a better understanding of how language can be modeled. And I found that other areas can often be better sources of inspiration than my own for this regard. So, keeping these goals in mind, let's dive right in. So typically when we talk about NLP, we're really talking about a wide collection of tasks that were designed to approximate properties of language understanding that we thought were important. So this might include things like text classification, so often assigning a single label to a set of words that make up a sequence, such as when we try to predict the sentiment of a sentence, or sequence labeling, where we can assign a label to every single token in a sequence that we provide, such as in a famous task called part of speech tagging, where we assign a particular part of speech to every word in a sentence. And then also more complex and newer tasks, such as spam prediction, which is actually linked to a lot of modern search engines that answer questions, or text generation, where we produce full sequences of text from some type of input. And these are more complex formulations that require even deeper semantic understanding of language. And since the start of the statistical methods era, the main method for tackling these types of tasks was to define the task in the first place as some closed formulation of what we want to do, annotate a large enough data set for it that we could train some machine learning model on it, and then measure how well we did with some evaluation metric. And that approach has been what we've been doing for the last 20 years or so. And it's what really enabled us to achieve and measure incredible progress over the last few years, as we made tremendous progress in scaling NLP models to never before seen sizes, which seem to unleash some insane generalization properties to emerge when training on small data sets. And over here, you can see this big model from this diagram that was taken a few years back. This is around 10 times smaller than this GPT-3 model right here. So, we can't even show it on the same scale. And now there's models that are around 10 times bigger than that one. So this is roughly 100 times smaller than the biggest models that we have today. But, that model, none of us can probably deploy on our own. And this incredible scale allowed us to solve many. Okay, these slides are kind of small, aren't they? All right, thanks. Allowed us to solve many of the data sets that we had designed to approximate some of these tasks. So here you can't really see this, but this right here, this number 6, is human performance on a collection of tasks that are designed, and we have roughly 6 AI models that are better than that, which seems a bit surprising at first glance. And it should be surprising, because despite all of these advances, it's clear that something is still missing in NLP models. While we're acing these benchmarks, none of you are interacting with your phone or with the speaker in your house the same way that Tony Stark does in Iron Man or something like that. There's still clearly a pretty big gap in terms of the type of communication we can have with AI systems, and what I just showed you we should be able to do right here. And so the leading reason why that is that when we work with these data sets and train in these closed loop frameworks, we're essentially approximating these tasks the best way that we can, but we're really removing the entire human goal aspect of what it means to understand language. Really, we're simplifying these problems down to merely encoding content that is explicitly written out, and we're ignoring everything about why we're trying to communicate that in the first place, which is the true reason behind communication. So, to illustrate this a bit more explicitly, let me give you these 2 sentences. It's going to snow, so I'm going to have to wake up 30 minutes earlier. I'm guessing that even with this very limited narrative, each of you is able to make these 2 statements make sense to you. They make sense with respect to one another. You're, able to recognize that there is a ton of important information that is probably missing in order for this to make sense, but you're also able to quickly make some intuitive inferences based off your personal experiences that are able to kind of fill in the gaps. So for example, if you have children, you might need to get them dressed for the cold, which could be quite a challenge. If you have a car, you might have to clear the windshield, heat it up, potentially dig it out before leaving. If you take public transportation, that could be its own disaster if it snows. And finally, with all these different inferences that you make, you're going to kind of aggregate them all together and settle on a new picture of the situation based on reasoning over these unstated but imagined implications, which makes this narrative coherent. And so the key question becomes then, how can we get machines to be able to understand text the same way that humans do? By recognizing that information is missing, by being able to fill in the gaps with intuitive inferences, and then by being able to reason over these inferences first in order to arrive at conclusions. And so what I'm going to posit here in this talk, and what I generally work on in my group, is that there's 2 high-level challenges to being able to do this effectively. The first is, how do we actually represent common sense knowledge for machines at scale, such that you can access these types of intuitive inferences that you need to make in order to fill in many of the gaps in order to understand language. So I mentioned that we rely on this shared context when we communicate, which allows us to elide information about world state. Well, it turns out the amount of things that we're able to kind of remove from the discussion we communicate is quite large. If I hold up a basketball here, I don't need to tell you that it's going to drop if I let go of it. All of you are aware of that. You have some basic understanding of naive physics. You know how people interact in social situations. So if I tell you that somebody had a bad reaction to something, you understand why that might be. And we really use all of these types of information daily to be able to understand the situations that we encounter, even if we never think about them. The second question is that how do we actually teach machines to kind of aggregate these types of intuitive inferences to reason about the knowledge that they are able to have? So in the example that I described earlier, we were super able to imagine multiple coherent narratives that were able to connect these two sentences. For machines to be able to do the same, in order to do that, they would have to be able to first identify which pieces of knowledge might be relevant to the situation, particularly amongst all the noisy pieces of information that they might be able to think are, partially relevant to it. And then they'd also have to know how to connect these pieces of knowledge together. What is the chain of reasoning amongst all these different little details, these little facts that they should connect together to be able to arrive at an understanding of this situation. Unfortunately, though, despite the incredible advances of the last few years, this is exactly the type of behavior that large-scale language models, which underlie many NLP systems, are super bad at. In general, when you actually train them to do a task, instead of learning the type of robust reasoning skills that we want them to, they learn the easiest patterns that they can pick up on that'll lead them to the right answer, often correlating simple relationships in their input rather than anything much more complicated. And so, I guess the best way to summarize this problem is that they do badly because it's easier for them to learn how to do badly than it is to actually learn how to do things robustly. By the way, I don't really want to besmirch machine learning models. Humans also rely on an abundance of cognitive shortcuts when we make decisions too. So we're just as bad at them, but we're okay with that, unlike with them, which we actually want to be better than us. So what can we do? Well, one approach would be to go back to good old-fashioned AI, or symbolic methods, as we call them. So these are classical methods that disentangle representation and reasoning and can give us high precision interpretable predictions, but at the expense of kind of being difficult to apply out of the box. So we often need very specialized engineering in order to fit whatever raw data we have to the schema that they use, and that makes them difficult to apply in open worlds. But there's a lot of advantages to them as well. They're quite programmable, they're precise, they're interpretable. And so really what we want is to be able to combine the best of both of these worlds, the interpretability and precision of symbolic AI systems and the expressivity and adaptability of neural ones. And so while my lab focuses on the challenges that underlie knowledge representation and reasoning in NLP systems from a practical perspective, our methodological focus is really on the design of novel neuro-symbolic algorithms that can combine the best of these two paradigms. And so today in this talk, I'm going to talk about two collections of projects that we focused on. The first on how neural models are actually implicit representations of world knowledge and how we can design algorithms that can extract, localize, and even modify this world knowledge within the model. And in the second part, I'll talk about how we can overcome some of the cognitive shortcuts that neural models learn from making predictions by using symbolic knowledge as a scaffold to guide learning how to reason. All right, so to start off, let's dive into neural models as implicit knowledge representations. And to remind everyone, the high-level challenge we're trying to solve here is how can we represent the large amounts of knowledge that machines need to be able to understand and use language in open world settings the same way that humans do. So first off, let's recap again how neural language models have changed the way we approach NLP and how they affected these changes. Essentially, the answer is kind of simple. They were trained on trillions of tokens of text and scaled to trillions of parameters. And that scale has really allowed them to become a go-to foundation for many applications in NLP, because this large-scale pre-training makes them a very good initialization for whatever goal we might be designing an NLP system to accomplish. One way to think about this is that if you want to design an algorithm that can answer questions, it's a lot easier to design an algorithm to answer questions than one that needs to learn English at the same time as it learns to answer questions in the first place. So when you're only focusing on one thing, it becomes a lot easier to accomplish. And one of the reasons that they become such a powerful initialization is that over the course of this large-scale pre-training, they pick up large amounts of knowledge about the world that they learn to represent implicitly. So in fact, if we take one of these models out of the box and just test it on its natural ability to predict the next word, given some type of preceding context, we can see this capability emerge. It predicts commonsensical continuations to the prefixes we give it. Are these slides kind of really bad? I don't know. Can folks actually read this at all, or it's good on the Zoom though? Okay, super. So for example, with this prefix, I want to learn to sail, so I bought a blank. It predicts things like boat, sail, canoe. Canoes aren't great for sailing, but you know, they're boats anyway. Meanwhile, if I change a single word in this prefix to I wanted to learn to drive, all of a sudden the distributions completely shift to things like cars, Hondas, BMWs, Fords. If I say I wanted to learn to read, we're not talking about books, Kindles, a copy of a book perhaps. And if I say I wanted to learn to fly, you know, the next distribution over the next word becomes planes, Boeings, jets. And so in each of these cases, all we've done is change a single word in this prefix, and that makes the model completely reevaluate its prediction of the next word in a way that actually exhibits knowledge about the world. And all we're doing here is what you may have heard of as prompting. So essentially you give the language model some prefix of text and see whether it can generate a continuation that is reasonable for that prefix. However, this isn't necessarily robust. So in fact, if you stumble across a case where the statistical associations that are kind of learned by the model aren't enough to understand the prefix of text that's given, the model is going to fail, such as in this case where I can change the prefix word to dance, and then the model produces at best irrelevant $10,000 house, US $10 pair of shoes, little kit, and at worst toxic outputs that I've censored for the purpose of this talks. And so, really the problem that we're facing here is that while language models do encode quite a bit of knowledge implicitly, which is what allows them to be used successfully in so many downstream applications, a lot of that learned knowledge is not reliably accessible. I'm pretty sure this language model knows what I should buy if I wanted to learn how to dance. It's just not telling me. So I have to figure out how to get it out of it. And this, kind of makes sense that it has trouble with it sometimes. All we've really done here is probe whether these language models can express knowledge when prompted with some language prefix that is supposed to reflect it. But this actually isn't what language models are designed to do. They're not trained to directly spit out common sense knowledge on demand. And so judging their common sense capabilities or their knowledge capabilities solely based on this limited interface may not be a true measure of how much knowledge they actually learn during this pre-training and might be able to access if they were fine-tuned properly. And so in our work, we draw a conceptual distinction between what it means for a model to encode common sense knowledge, so whether knowledge is embedded in the parameters of the model versus being able to express common sense knowledge, which mean at any point in its training, whether it can be expressed using the existing input-output interface that is currently on top of the model. And what we've seen so far is that prompting is quite good at letting us access knowledge that the model can directly express under its learned language abilities, but that this is actually quite limiting. So while humans use language to express knowledge, sometimes it's not its only purpose. So the real question then is, can we actually convert this language model's language representations, which are geared towards expressing, all of natural language, towards the more constrained expression of language that communicates knowledge directly and in a structured way, which would allow us to actually get a better sense of what sources of knowledge are available. And it turns out we can actually do exactly that. So as we showed in our AAAI 2021 paper, we're back. We can actually do it by exploiting properties of these language models. So, once again, well, I guess to give a high level overview of this, we're still exploiting the fact that these language models are trained on trillions of documents, trillions of tokens, and as a result, learn implicit representations of knowledge. I keep coming back to that idea because it's actually kind of super important towards understanding where the field of NLP is right now. It's, kind of scale all the way down. And so how do they actually learn this? I think it's important to note for what it comes next. Well, essentially, there's multiple ways of training language models, but for the purpose of this talk, we're going to focus on one of the most common ones, which is that we just learn how to predict which token comes next, given a set of preceding tokens. So what you can see here is that all of these tokens are actually offset by 1, such that for any sequence of tokens on the bottom, you're always predicting the next one in the sequence at the top. And what does that allow you to do is that once it's trained, if you give it a sequence of tokens, you can generate a sequence of follow-up tokens just by taking the output and plugging it back into the input in the first place. And that actually allows you to have a dynamic system where you're feeding your outputs from one step into the model at the next. And so once we have this pre-trained language model, what we can do to actually learn to represent declarative relationships is train it on examples from some symbolic structures, such as a knowledge graph. And that's going to allow the model to actually learn the structure of knowledge that we want it to be able to express. So more specifically, we can take tuples from this knowledge graph. One, let's say, that has a head entity, such as person sails across oceans, a relation such as requires, and a tail entity that connects to the head entity through the relation, such as buy a boat. And we can just provide the language model with the head entity and the relation as the input, and then train it to generate the words of the tail entity one by one, which is exactly what a language model is normally trained to do in the first place. So essentially, we're just training it yet again to predict the next word given the preceding sequence. The trick, though, is that now our inputs are providing information about how we're defining explicit knowledge relationships between these head and tail entities from the knowledge graph. And the language model is going to be able to learn that with enough examples. And in essence, we're really converting this language model that knows how to generate language into a knowledge model that can hypothesize knowledge just by retraining this language model on these examples of structured knowledge. And there's really a few important things to realize about this. First, our input here is only constrained by natural language. So we can represent any concept as an input to hypothesize common sense knowledge about. Once we've actually learned from these relationships, we can apply these relationships to any head entity. And second, because these models have been pre-trained on language, so the same set of symbols that we're now using from this knowledge graph, the model is going to have some existing intrinsic representation of many of the concepts that we might prompt it for knowledge about. And so we're going to be able to generalize the structure and the relationships that we learned from the knowledge graph to all of these other concepts that are not in the knowledge graph, but that the language model is able to represent implicitly. And that includes some very complex ones, which I'm going to get to in a bit. And so I guess, I'm not going to show any numbers in this talk because, the takeaway is just that we can do this fairly well. But I think, examples can demonstrate this fairly effectively as well. So here, for example, I can create a random head entity. Antoine presents at the seminar. There's not too many knowledge graphs that have that particular entity in them, as you can guess. And I'm going to give it to the knowledge model along with a set of relations from a knowledge graph that we trained this model on. And then we're going to be able to hypothesize different inferences about this particular entity, such as the fact that X here, being Antoine, might be perceived as knowledgeable, and that at the end, others will want to ask questions, which I'm hoping you do perceive me as, and that you will want to do by the end of it. But what was perhaps most interesting about this approach, which we had a follow-up paper at AAAI 2021 this year, is that this could allow us to hypothesize knowledge about a very complex entity. I don't have much time to get into it, but what we essentially showed is that you can actually use this method to generate common sense inferences about very information-rich contexts. So one of the classical issues with symbolic resources, which I hinted at earlier, is that you need to standardize your input to fit it to whatever schema your symbolic resource is organized in. And that can, cause you to, one, have trouble actually finding the right links to the symbolic resources in order to access information. And two, you're going to lose a ton of contextual information about what your raw data actually represents because you need to compress it in order to make this connection. But once you have these knowledge models, there's actually no more linking to any type of static knowledge base as you would have with a symbolic resource. And there's no more losing as a result of this important context that you have. What's exciting too is that you can actually, broaden this even further. So if you think about what the knowledge model is doing here as it takes this context, is that it generates new common sense inferences about this context. And so we can kind of view that context as some type of root node in a graph, and the generated inferences about that context as new generated nodes that connect to it. And in essence, what we're doing is that we're creating this dependency graph of common sense knowledge about this root situation. And then we can actually scale up this approach. So the same events that are generated by this knowledge graph, when you fine tune to make it into a common sense model, do you lose information? I'm going to come back to that at the end of this section, because that's an important question. So the same events here that we're able to generate, we can now generate new knowledge about, and that kind of allows us to grow this dependency graph of common sense knowledge to really have a larger symbolic world graph of information that is contextualized to this original root node. And so what you can do then is that if you, let's say, have a set of pre-initialized conclusions that you're trying to evaluate, such as, let's say, answer options in a multiple choice question answering task, or end states in some type of decision-making process, we're usually trying to decide between two alternatives, not just trying to decide between any, state of the world we can go into. You can also connect those back to this graph that you've created as leaf nodes. And in this way, you kind of have some intermediate states, which in this world graph, but your root node kind of remains this original context, and your end states, remain the leaf nodes in this graph. And in essence, what makes this really interesting is that we've now constructed a symbolic graphical representation of the world that is grounded to common sense inferences about this original situation that we had. And now we're actually kind of moving back and forth between these neural and symbolic states in an interesting way. So we started out by embedding a knowledge graph inside a language model. And now we're using that to reproduce some symbolic structure about any situation that we provide to it. And that allows us to really get interpretable representations of the world that are much richer than what we would normally get by using a symbolic resource. And so while I don't have time to kind of talk too much about the effects of this today, this flexibility has allowed this technique to become fairly widely adopted for presenting latent common sense inferences to downstream task systems. So in many places where we might have used the traditional knowledge base to provide external knowledge, or where we might have ignored the problem altogether because there was no way to really tackle it, now we can use these dynamic knowledge models to provide an interface to these contextually grounded common sense inferences. So people have used it for things like therapy chatbots. Oh, there's a typo there, too bad. And things like designing new types of text-based games with richer world states. So do language models have common sense? Well, I guess on one hand, it seems clear that they can't reliably express it right out of the box. On the other hand, when we actually start training them on a few of these declarative relationships, they're clearly able to leverage pre-trained representations to learn how to hypothesize knowledge much more broadly than whatever was in the symbolic resource we originally designed for them. But unfortunately, we still haven't solved the main problem that we were trying to, which is that we haven't kind of moved on from a particular confounding factor, which is, what does it actually mean for a language model to encode knowledge? Does it mean that they actually have discoverable representations of knowledge? So I can go in there, grab a few parameters, and translate or decipher those parameters to some sequence that represents something symbolic? Or does it just mean that if I train on new data, I can generalize fairly effectively from the facts we see when training on the knowledge graph? And so we investigated this as well. In a paper that was published at AKBC 2021 this year, we looked at how these knowledge models change internally when trained on examples from these knowledge graphs to be able to kind of attack this question a lot more rigorously. So just to, I guess, motivate this part, I want to take a quick step back and talk about what these transformer models look like internally, because it's going to be slightly useful for what comes next. While there are different transformer architectures that exist, they are kind of typically organized in this following way. They're made up of some type of encoder and a decoder, at least of their sequence-to-sequence models. And then inside their encoder, they have some self-attention network, and then followed by a feed-forward network. And in a decoder, you have some self-attention network, then a cross-attention network, which looks at what the encoder output is, and then some feed-forward network again. And what attention typically does is that it mixes the representations of different inputs to the model. So if you have a multi-token sequence, it allows all those tokens to look at the other tokens in the sequence, make a representation of it, and then formulate kind of a new idea of what that token is supposed to mean. And then the feed-forward networks, as with typical neural networks, just provide some type of expressive capacity to the overall model. And then to get a sense of how these models learn to represent knowledge, we looked at how these parameter matrices, so the ones that actually make up these feed-forward networks and these self-attention layers, change during fine-tuning by measuring different types of distance functions between them. And one of the most interesting things to note, there are kind of many results in the paper, is that most of the parameter change in these networks is actually happening in the attention heads, in both the encoder and even more specifically in the decoder. Highlighted here by these kind of blue rectangles. So here the darker shaded squares indicate more parameter change for a particular parameter type at a particular layer. And so this is interesting because our fine-tuning procedure, when we train on all these knowledge graph tuples, mainly modifies the functions that mix different token representations and that pass messages between the encoder and the decoder. But it barely modifies these feed-forward networks at all. And why might this be important? Well, it's tough to know, but there has been prior work that's kind of looked at what these feed-forward networks are supposed to represent, and actually showed that many times they serve as key value memories over information learned during pre-training. So when you look at sequences learned during pre-training and learn from them, you can actually access or activate those sequences very specifically by looking at the feed-forward networks of these transformers. And so essentially, if we accept this finding, we're decomposing the transformer block into two components: attention functions, which change a lot and are the compute engines over inputs, which help you form an access key to the memories in the feed-forward nets. And then your feed-forward nets, which are de facto memories of information that have been learned during pre-training in the first place, and that you're now able to read from when you do forward passes. And what this seems to indicate is that fine-tuning allows your transformer model to learn to access previously memorized information rather than learning new things to memorize over the course of fine-tuning. So you're essentially learning how to access things that you already know in different ways, which seems to indicate that you're not actually doing generalization, you're doing memorization when you actually do this type of fine-tuning on knowledge relationships, which is exactly what we want to be the case if we're hypothesizing that these large-scale language models are knowledge engines in the first place. And so the last thing I want to discuss in this first part of the talk is a ramification of this conclusion, which is that if you can do these types of targeted reads of memorized information during fine-tuning, can we also learn to do targeted writes? We're obviously all computer scientists. We like reading and writing information to memory, and we want to be able to change what information is in this language model. So in yet another recent work that'll appear in iClear 2022 this year, we actually proposed a method for targeted edits of the internal representations of language models. The reason I'm kind of going through all these papers is that it's to kind of tell a high-level story, but to also show you the breadth of what we try to work on in understanding the knowledge representations of these systems. So I guess the reason we wanted to do this is, once again, when comparing neural systems and symbolic systems, one of the big advantages of symbolic systems or knowledge graphs is that it's super easy to edit any information in them when it becomes outdated or incorrect. It's essentially a database. You find out where information is stored, which you can very easily do. And once you do that, it's fairly trivial to change the value. With neural systems, that's not at all possible. You've compressed all the information that you trained on into these parameters, and then you kind of don't really have any idea where it's stored or where information is actually encoded. And so in this work that's going to appear at iClear, we developed new meta-learning algorithms for being able to update models with new information using only a single training example. And so that avoids this fine-tuning problem, which spreads out information wherever it can go, potentially overwriting, potentially just adding new content that interferes with what was previously known. Here we can become much better at actually overwriting this information so that we can predict correctly the next time around. And what was especially important about this approach is that we could apply it to incredibly high parameter language models, tens, if not hundreds of billions of parameters, and it doesn't actually require you to retrain the model itself. Only the update functions have to be learned, which makes it really flexible to apply. So to conclude this part, and then I guess we can jump to a few of the questions that have been asked. It's pretty clear that these models are learning to encode decipherable knowledge representations during pre-training, since we can learn to access that knowledge and see how the parameters change in the memory component of these networks. And so, what we really needed to discover this, though, was having symbolic representations be available to serve as scaffolds for accessing learned knowledge and being able to measure it in the first place. And more importantly, one of the things that we're thinking about now into the future, beyond developing better methods to make this more rigorous, is how should we design future symbolic resources if being able to transfer from neural models is kind of a new use case that unleashes all of these possible capabilities. So are there any questions now that we're wrapped up here? I think there were some in the chat.
Yeah, 2 in the chat.
All right, so I'm already at 40 minutes now with the questions, so we're going to zoom through the next part of this talk, which is actually about one of the, what I don't view as a shortcoming, but one I don't like about the first part of this agenda, which is we're kind of getting rid of the structure of all of this. We have these tuples that we're using, that we're training this language model on in order to get it to be able to express this knowledge. What that does is effectively throw away all this rich structure that is in these knowledge graphs and just kind of, taking little snapshots of these knowledge graphs in the first place. But really, knowledge graphs are, more than just the individual tuples that make them up. They provide kind of this much richer approximation. And so, another question that my group focuses on is whether this structure could actually be useful for addressing the second challenge I described earlier, which is how do we actually teach machines to reason about common sense knowledge? And so why would we want to do this in the first place? Why would structure be useful in the first place? Well, I showed this slide at the beginning of the talk that said that neural models are unreliable predictors. And this is kind of a result of a central issue with training these neural models, which is that the data sets we use to learn or adapt them are really just snapshots of the full problem that we're trying to solve. And the examples we collect are often similar in unintended ways. And so when we train these models to make connections, they typically exploit the simplest patterns that they can, some things that we may not have foreseen, such as biases, annotation artifacts, just, maybe we use common words in the examples that we annotate, and they don't actually learn the semantic or, abstractive underpinnings of the task they're trying to solve. So even if the model is able to encode the background knowledge that it needs to do a task, which we've shown they may already do, it might not learn to connect the dots between those facts or leverage the right internal representations to be able to answer correctly when fine-tuned to do a particular task. So as an example, if we look at this common sense question answering question, if it's not used for hair, a round brush is an example of what. Typically, if we were to have a language model answer this question, what we would do is that we would give it as input to the language model, get some output at the end out of it. I guess I can use my mouse to show this for the folks on Zoom, and then use that representation to compute a score for each possible answer. Now, the thing about this is that I think we can all kind of say that a language model that's been trained on billions of tokens of text has probably encountered, paintbrushes and knows that round brushes might be used for art supplies. And in fact, if we use the same knowledge model approach I described earlier and ask it, what does it think about round brushes? It actually shows you right off the bat, the first thing that it can use a round brush for is to paint a picture. And yet, if I ask it, after fine-tuning this model on the Commonsense QA dataset to answer this question, it gets it wrong. So even though we know this model has the necessary knowledge in order to be able to answer this question correctly, it doesn't successfully adapt during its fine-tuning phase to actually be able to learn how to select the right question. And so really the question we're interested in asking ourselves is, moving beyond the fact that neural models find easy shortcuts that don't allow it to generalize, and the fact that yet again, we can't use symbolic approaches because they lack the expressivity to be able to apply to whatever raw data we give them, how can we actually use the structure for symbolic methods to ground neural processing? And as a quick example of how we do this, I'll discuss our work from NACL last year, QA-GNN, which is actually a fairly simple idea for unifying language models' knowledge graphs and kind of treating them as equal participants in a reasoning process. So all you really do is that when you're given an example provided by language here, unlike before where you might just process it with your neural model and get some type of representation of the output, now you also use it to extract some type of local graph of common sense knowledge. Maybe you're actually using a static knowledge graph that's already been annotated. Maybe you're using one of the knowledge models that I described earlier for hypothesizing something. And then as before, well, actually now what you're going to do is that instead of making a prediction from it, you're just going to use it. You're going to use that initialization we got at the output to initialize a new node in this graph, which you're going to connect to the entities from the extracted knowledge graph that you have using some type of special relation types. And what connecting this representation of language to the graph as an additional node allows you to do is to get this joint graph representation that brings them together into a shared semantic space. And so naturally, now that you have a graph, what can you do with it? Well, you can represent it as a graph neural network and initialize a set of features or initialize a vector of features for each of the nodes and then propagate messages between those nodes over multiple layers. And that's actually going to learn to simulate the reasoning needed to be able to answer these types of questions, but it's only going to be able to do it along the predefined structure provided by the knowledge graph that you have when you extract this KG from the text. And so then I guess to give the full pipeline, given some type of context written in natural language, you're going to retrieve a subgraph of entities, compute initial node features for each of the nodes in that graph, compute some language encoding from the language model, and then combine them together in this shared graph structure. And then you're going to mix the knowledge from both modalities over the course of multiple layers of message passing in the graph neural network. I'm not going to go into too much detail about what the message passing algorithm looks like, just because I'm running out of time. But I'm happy to talk about it more offline. But essentially, it's an attentive function where you compute some type of message for each of the nodes, and then an attention for how each node in the graph attends to the other nodes. And then you can integrate this model into a larger pipeline for a particular task. So in this case, we can answer these types of tricky questions about common items, such as the one that I used to motivate this. And so really the power of this method is that it's really able to exploit the fact that symbolic structures can really provide knowledge in a format that makes reasoning relationships easier to learn for neural models. Why is this the case? Because that's exactly what we define symbolic structure to do. They represent knowledge graphs, they represent logics, but the problem with them is that you're losing, let's say, the nuance of the original situations that you're encountering when you try to map them directly to these symbolic resources in the first place. And you really need to be able to maintain these if you want to be able to operate in open worlds. And so what we proposed in this work was, kind of a simple approach to be able to initialize these these sequences described through language as additional nodes in a graph, which allows interaction between both modalities. And so if you have structured resources, this is kind of a simple way of taking your raw data, representing it neurally, adding that to the graph structure, representing both of those together neurally, and then coming up with new ways of reaching conclusions. And we subsequently wrote a follow-up paper to this work that's going to be presented at ICLR this year, and that just kind of improved on one of the shortcomings of it. But that I'll skip the details of. These are kind of the questions that we've been able to see this kind of method sort of do, general world knowledge, but we can also do much more complex things with it as well. So it's not just about kind of answering simple questions about the world. You can also answer questions that require a whole bunch of knowledge to be brought in, but also with very kind of carefully selected details about what's being expressed in language at the same time. And across these very different domains, we kind of see clear improvements across the board by using these joint language and knowledge methods, as opposed to only using language in the first place. And in fact, we have another paper coming out soon that actually gets an additional, I think, 6% improvement on the right, all the way on the one all the way on the right over there. I guess the last thing I'll mention, though, is that what's perhaps even cooler, though, is that these architectures allow us to track how differences in the way we express reasoning induce different graph propagation schemes across time. So here, for example, given this exact same question as before, if it's not used for hair, a round brush is an example of what? A hairbrush or art supplies, we can look at the starting attention over these two entities in the knowledge graph and see that it's kind of split between the two. But by the end of it, it's really focusing more on the round brush as opposed to hair, even though they were both entities in the context. And meanwhile, round brush now is almost solely focused on painting as opposed to hairbrush, which is exactly what we would want the attention to focus on if it was reasoning over this situation correctly. But correlation is not causation. So taking a bit more of an intervention perspective on this, If I actually remove the negation and say if it is used for hair, a round brush is an example of what, now all of a sudden it's pretty much focused solely on hair as opposed to round brush, which is what we would want it to do if we were going to have this be correct. And finally, one last perspective is that if I change hair to art and say if it's not used for art, a round brush is an example of what, once again, by the last layer now, most of the attention is on round brush, but now instead of painting, round brush's attention is much more associated with hairbrush. And so in essence, changes in the language that the models read is reflected in the way the nodes in the graph neural network receive and process information, which allows us to qualitatively examine how reasoning steps are being reflected by the model. So in conclusion, one of the big challenges that my group tries to, address is that machine learning models often shortcut very complex behaviors, such as reasoning and the types of intuitive inferences that we as humans make when we encounter situations all the time, because they learn to exploit simple statistical regularities in the data that they're trained on. Meanwhile, symbolic inference methods, can't be used out of the box because they tend to lose the contextual nuance that we need to actually really understand situations, and just have too much of a compressive effect to be used successfully, which is why they fell out of favor over the last 20 years. And so really, the focus on my work is how we can use symbolic resources as effective scaffolds to more efficiently and reliably learn complex behavior while keeping the adaptability of neural systems. So on that note, thanks for taking the time to listen, and thanks to Jan and the CIS team once again for having me here. I also want to thank all these great folks, my group at EPFL, and then collaborators at the Allen Institute and Stanford that worked with me on these great projects. And if we have more questions, I'm looking forward to take them, and even more, I'm looking forward to working with many of you in the years to come. So if these topics interest you, get in touch with me, and yeah, hopefully we'll work together. Thanks again.
So just some brief words. Thank you for all of you here on site and online. Thanks, Antoine, for the presentation. Very interesting. Next opportunity to attend the CIS event is already next Monday. We're looking forward to the CIS colloquium with Professor Philippe Rigolet. The title of his talk is Optimal Transport for Statistics and Machine Learning. If you manage to come in at EPFL, it's going to be at BM 5202. That's in the STI building. And promise there's going to be a nice upper afterwards. Thank you. Stay safe. Goodbye.